Welcome to the second episode of Cutting Through AI. Today's topic is going to be machine learning. And the aim of this lesson is for you to understand how we can use past data to predict the future with a technique called machine learning. And you will also start having an understanding that why the main advancements on AI that we have seen are in scenarios where we have massive amounts of data sets, which are text, so books and the whole of internet, as well as images and videos. This is also for you, perhaps a business person, to start understanding and trying to implement AI in your workplace or in your business or in general, why the importance of collecting data and having significant, clean data that can predict something, it is crucial, and why no matter how much data you can have terabytes or petabytes of data. If this data does not have a link or a correlation to the thing you want to predict, well, it is virtually useless. And I will help you understand why this is and how it all comes together. I won't go into any equations, but I'll help you understand why we'll use GPUs, why there's a GPU boom, and why GPUs are so important in this AI era that we currently have. So without further ado, let's start. Let's imagine that you're the owner of an ice cream shop. And let's say that you need to know how many employees you're going to put in your shop depending on the number of clients that you're going to have. You don't want to have 10 employees when only 5 people are going to show up for the day. So you want to optimize your resources like a good business owner so you can make as much money as you can, keep the costs low, and be as effective as possible. You've noticed that every time it's warm outside and the sun's out, that the number of clients increases significantly and you have to put more employees to serve them. And you've realized every time it gets cold, you have less people coming to your store. As a good business owner, you've been recording exactly the relationship between the temperature, or in this case, I'll use the standard scientific of Celsius, with how many people are coming to your store. And you want to use this relationship and this past recordings that you've had for you to be able to predict the demand of customers in the future, and you can assign the correct number of employees so you have the most efficient lean business possible in terms of employee to customer, so you can make your money and cut your costs. You decide to take the mathematical approach and you decided to plot these values on a graph. You've realized that when the temperature is high, that you have a lot of people coming in. And you realize that as the temperature starts dropping, that kind of less people start coming in. So it starts becoming something like this, but sometimes it's holiday, so we can have something like this. But that in general, the number of people coming goes down as the temperature goes down. Now you need to be very accurate. There's a big difference in cost and customer satisfaction if you miss one or add one employee extra. So you really need to be accurate, and it's important that you are as perfect as possible with the data you have. How would we do this? Well, we see here we're trying to predict a Y. See here the customers in relationship to a feature or something, which I would like to call X, which is our temperature. And the really important thing that you're trying to figure out is, what is the relationship between X and Y? Is it 2 times, 1 time? How much do I have to multiply or divide my temperature to get an accurate estimate of the number of people that I have? And I would like to call this relationship M. If I know my M, then with the temperature, I can just plug it in and I will know exactly how many people I'll have on my store, and I will be able to put the right amount of employees and make the most money as I possibly can. This is where machine learning shines. Machine learning is the process of using our past data here to find the relationship between our features, in this case temperature, but it could be more. It could be temperature plus if it's raining or not, but we'll keep it simple and just use temperature. And use our features to predict a target variable, which in our case are the number of clients. And finding the relationship between our features and our outcome. Again, as I've mentioned in the introduction of this video, If I decided to take what I would like to call a useless feature, right? So for example, instead of having temperature, I'm trying to predict the number of bananas sold last month as a feature instead of temperature to predict how many people are coming to my ice cream store. I think we can all agree that no matter how many years of records I have and how accurate I have of the quantities of bananas sold last month, that I will never be able to predict with any accuracy how many people are coming to my store. Maybe if I have a banana flavored ice cream. So this is really a really important point that I wanted to hammer across all of non-AI people or non-data scientist people or non-machine learning people, is that the features you choose and that you have are essential to the quality of your predictions. I would like to say it is way more important than the algorithm or the machine learning method that you're going to use. The main factor for success on any AI application is the data that I have, my features correlate or give me the recipe, or are they the ingredients that will allow me to combine it all and predict the thing that I want to predict. There's also another very important aspect, which I will just demonstrate you in a few minutes, is that I need to have enough samples that are true, that are accurate, right? Because if I have then bad data or fake numbers, then my relationship that I will derive will probably give me a wrong outcome, which will not match reality. I need already two things here. I would need, number one, features that actually correlate or explain my outcome. And number two, I would need some historical data, which is accurate, which is not tampered with, which we like to call in the industry clean data, truthful data. Assuming that we have our clean data and we have a good suspicion that our chosen features, in this case, temperature to people going to the ice cream store, which I think is a very good relationship, how can we find the perfect M, or the perfect relationship between temperature and customers? What method can we use? What can we do about it? Well, very simple. First of all, just visually, we can see that if we kind of drew a line here, though not absolutely perfect, as you see here, we're a bit off. But nevertheless, this yellow line here would give us a pretty good prediction of how many people are coming in, no matter the temperature that I have. Once I know my line, which can be described by this equation here, y equals mx, especially the m, I'll be able to, no matter what temperature or no matter what x, to find the correct y. And this, again, is a very important aspect that I want to hammer on. Machine learning, at its core, is just you collecting all the possible features that you have that represent your outcome, and then you will find the line of best fit or the best line through them that represents the most accurately the outcome that you want. But then you're perhaps wondering, okay, what does that mean? What does it mean to have the most accurate line? Well, the easiest way to do this is to use your past data. So let's imagine that the points that I have here are represented by this table. And we have that this point is, let's say, 30 degrees Celsius, and let's say it's 130 people. Just write it for you. Have something like this. So then what my machine learning algorithm will do is that, remember, we want to find M. M is the most important thing that we want to find. And the easiest way to do it is just start randomly. We'll just do a random value for M and see if it's matching. If we set M equals 1, then we're saying that our temperature times 1 equals Y. So we look here at our truth table and we try to see if it's matching. So we are saying that if M equals 1, that 1 times 30 should give us the right number of people. And clearly, when we see here that 30, which is the value we have for temperature, or here, is not matching 30 people. We would be around here and we start seeing that we are miles away from the truth, 100 units from the truth, right? Because I am predicting that it's 30 times 1, but the true value is 130. So in mathematical terms, what I could say is that I will get the true y, so y true, minus my just fake predicted y, and this will give me my error. So in this specific case, since I'm doing with 30, I know that the true value when the temperature is 30 is 130. What I predicted with my m equals 1 is 30. So here I see that my error is 100 points. The trick to machine learning here is that some very, very smart people, they figured out an equation where we'll get you the error, and they know that what you want to do with the error is that you want to make sure that whatever you're predicting is as near as possible to the truth. So what we want really, ideally, in a good world, is this to become 0. And what some smart people have discovered is that they've managed to put this equation that tells you how much you need to change your m based from your starting point, in our case 1, to get this error to 0. So what this equation will do is that will tell you, okay, you're actually plus 100 off. So maybe what you should probably do is that you probably need to add a bit more to your m. So then what I'm going to do after the special equation is that this equation is telling me you should probably increase your m. So what I'm going to do now is that after my first try here, I'm going to go ahead and I'm going to increase my m by 10, let's say. So now for my second attempt, I have to cross this line because I already used it for my test. Now I need to use a new sample, right? So now what I'm going to do is that I'm going to try to predict again with my updated m. 25 times 10 to see what value I'm going to get. So here I see that I have 10 times the new temperature, 25, that equals 250. We see that the true value is 110. So now we know that I'm a bit off, but let's see by how much am I off. So my y predicted was 250, and my true y given the 25 is 110. If I plot this on my graph, so here 25, this time I overshot by a lot. Let's assume I'm here. We can see here that I am way off with my m. And then what I will do is that I will use the special equation again. And this special equation will tell me, hey, honestly, you see here, you overshot a lot. So you really need to probably reduce your m. Remember, I want my error to be as close to 0 as possible. And right now I am 140 off from my target. What I will do is then I will cross off my second attempt. I will reduce my m. Maybe we can say something like 5. And I will try again to see if I'm matching with my next data sample. Then I will go and see my 20. My m equals 5. 5 times 20, which is the temperature. This is my m, temperature. I get 100. I will go then and see the true value, 90. And whoa, all of a sudden, I'm way, way closer to getting the truth than I've ever been before. So what I will do now is I will see that my y predicted is 100. What the actual true value is 90. So now my error is only 10. And I'm way, way closer than I've ever been before. And that's just from 3 samples. So then I will go here. I'll get my 20, my 90, and I'll see that here now I am a bit off, but not by much. And the important thing here for you to notice, and because we will repeat this on and on and on in machine learning, is that by every time I'm looking at past data, I am effectively trying to get these errors here as small as possible. I want to make sure that my predicted points are as close as possible to the truth so I can get my M that will give me the best line or approach the relationship that this yellow line is giving. And the way that machine learning works is that I'm going to go through my entire data set and I'm going to keep trying to correct on and on and on until all the errors of each point that I have are the smallest as possible. Because if I have very little errors in my predicted values, it means that I'm probably at the most correct or closest M matching my reality. And once I have the M, well, I can calculate pretty well how many customers I'm going to have on my store. And this whole process that I just showed you is called gradient descent. In our example, we just used one feature. But in most cases, we'll use way more than one feature. We might use 5, 6, 7, 8, 9, 10, 12. But as humans, we can't visualize it. The most we can visualize are 2 features. And how would that look like? Imagine I have my number of customers from my ice cream shop, but now I also add another feature apart from the temperatures. And I'll add here another axis representing if it's raining or not. If I have the temperature then, and if it's raining and the quantity of rain that I have, and I'm going to use it to predict how many people are going to be in my store, well, then all of a sudden, now I can have that my z-axis here is 3D now, will be the amount of people that I want. My temperature and rain combined will help me predict my z. So my equation now will be looking something like this. It would be the number of people in my store will be a relation of the relationship between my people and the temperature, call it M1, plus the relationship between my number of people and if it's raining or not, and we'll call it M2, and let's say R for rain. And here you see that I can represent them by points, so I'm going to try to find my M1 and my M2 by plugging in past points of my temperature and my rain and checking what happened on that combination of day. I will still use my machine learning algorithm that I just showed. I will try to start with some random values for M and M2. And then I will plug into the special equation that will iteratively get me to the truth and get me to the line of best fit. Now, what happens if we don't have enough data to reach the best M possible? Well, you will have an inaccurate M. So if you don't have enough rows or enough iterations to correct your algorithm so you can get the M's that represent the truth, you have a model that's worse off. You have a worse predictor. This is just life. This is why models that have a lot of past data to train on perform way better than models with insufficient data. And in many cases, not having extremely good results automatically makes a model bad. For example, if you had a model that was classifying based off X-ray images if someone has breast cancer or not, it is not good enough to have a model that's 85% of the time right. Even though 85% right seems pretty good, you cannot risk the lives or the healthcare of the 15% of people that they're going to get wrong. So here comes one of the main problems, or I would like to say restrictions, on business applications of AI, is that a lot of times good enough is not good enough, which means unless you're extremely accurate, for example here 99% plus, and you're accurate in a way that's okay. So for example, using the breast cancer example, if the few errors that I make are breast cancer but you actually don't, this is a mistake that I'll be kind of okay with, because then you'll just do some extra checks, human verified, you'll see, oh, it was just a false scare. The unacceptable error would be if my patient actually has breast cancer and I predict that they don't, because then they don't do the extra checks and they have consequences on their health. This is, as a practitioner or as a user of AI, a very important thing to understand, is that sometimes just being good is not good enough. You need to be excellent depending on your use case. In some other cases, it's okay to be a bit off. And this is really something that I want you to start thinking critically on your use case is, okay, if I'm going to use AI, how accurate do I need to be for it to be useful? What are the risks if I'm not? And what kind of wrong is okay with me? If you're able to use this on your playbook, you're able to use this on your work or in whatever usage that you have all the time, I guarantee you'll be in the top 5%, if not 1% of people using AI for practical purposes. If you can combine this with what I just taught you about having the good data, having data that correlates with what you're trying to predict, you are then, again, golden. These are some very important things to keep in mind. And they are in every application, what I would like to call of in-house AI, right? You're using your own data to use your own AI models, and you're using techniques which are not seen in what we call Gen AI, right? You're just using some standard techniques, which you might have heard of, just this machine learning. The specific case is gradient descent, but all the other techniques, random forest, XGBoost, perhaps you've heard of them, perhaps you've not. This is very essential because in my experience, in my work life, I've seen many projects being doomed from the start of there clearly not being enough data to train a significant model that will meet the business requirements of the business KPIs. My banana quantity example. Doesn't matter if I know how many tons of concrete have been laid every day. I can have the most accurate and most extensive data set on earth on the amount of concrete that's been laid on my town or nearby my store. This will not correlate with the amount of people wanting ice cream. So again, for the last time, I know I'm beating a dead horse here, but you have no idea the things I've seen throughout my career. So it's really important that if you're going to implement an AI project in your business, in your work, that you are aware of these three factors, which is the availability of data that you have, the quality of data that you have, the accuracy, so it correlates and it's truthful, it's not made up data. And third, how accurate you need to be. If those three factors are not combining, or you have basically green lights on all three of them, I would highly recommend you to not proceed with your project. It's going to be a waste of time. It's going to be a waste of money. I promised you also that I will help you understand why we use GPUs. Since the real world is not perfect, in all the data sets you'll ever had, you're going to have what we call noise, or basically impurities on your data. So even though, let's say, the true temperature is 30 degrees Celsius, but let's say your thermometer is a bit off, so it says it's 31, 31.5, and then, or you're collecting your data over a course of 2 years, and then you change the thermometer in the year one, and your second thermometer is reading things a bit differently. Not by much, but let's say 0.3 or 0.4 or even up to 1 degree different than your previous one. You still want to be able to reach your accurate predictions. So you need to start generalizing a bit more and basically making your algorithms a bit more resistant to noise. If you take every single line at core value to update your M's, the noise is going to really affect the values. You need to be able to train your model as fast as possible on all this huge data, because we don't have all the time of the world, and it can be very, very, very inefficient or very long training times depending on the amount of data you have. Some organizations will probably have petabytes of data, terabytes of data. So we need to be smart. So we need to solve the noise issue, right? We need to generalize our predictions, and we need to be very effective with our calculations. So if we take a CPU, which is sequential, it goes one by one on every line of data, will take forever, and it doesn't help us with our noise. What they found out is that a more efficient way to do is, if you have a data set like this, instead of reading line by line and then applying the correction on your M every single line, what they found that they can do is that they can calculate the errors for batches of your data set at a time. So let's say our batch has 3 rows. I'll calculate my error 1, my error 2, my error 3 given a specific M, and then I'll just divide or take the average of my errors to get a mean more truthful error that's more resistant to noise because I'm taking the average. And what they've managed to do is that if I then do this for one batch, but then I calculate my average errors for all the other rows, let's say 3 to 6, and then 6 to 9, then I can then later average this, and then the correction that I send to my M is resistant to noise, and I'm basically doing kind of a approximation. I'm saving a lot of time by not having to go back and forth to reach the good M. Every step I'm taking towards the correct M is more resistant to small variations or to bad data, and at the same time I'm seeing more of my data set to give better quality corrections. Now, the big issue is that if my batch is too big, then I am risking that my corrections on M are inaccurate because I am generalizing. I'm seeing everything at once. I'm not able to approach the correct value. But they've also realized that with this batch system, which is to help against noise, they can kind of do them at the same time and correct them parallelly. So instead of having to go now one by one and correct their M's like this, what they figured out is that on the same time frame, so in the same second, they can send and process all the batches in parallel, and then they can make a significant update on my machine learning algorithm. I found that GPUs were originally made to display pixels on your screen, and if you take your screen to be something like this, each pixel here has a specific value which represents the color that they have. It's usually a combination of red, green, or blue. And what happens with GPUs is that since they have to present the colors on your screen simultaneously, is that they have to compute the pixel value of every tiny bit or every tiny pixel on your screen kind of independently or in parallel. Each of them will have their own color combinations, and the GPU does not have time to go one by one, or else you would have a massive delay on your screen. It would not make any sense. What data scientist researchers found out is that they could use this property of the GPU of parallelization, or making these calculations at the same time, where that instead of pixels, you can kind of send a batch and leverage this infrastructure of parallelization to calculate all your batches at the same time. This gives massive gains on the speed of machine learning training algorithms. And this can be, guys, in my experience, it's not only one time or two times or three times, this can be hundreds or thousands of times faster. This is one of the big reasons we're having this GPU rush or this NVIDIA rush, is this act of parallelization, which allows us to train faster and more accurately. To finish off this video on the introductions of machine learning, I would like you to realize that so far all the features we had on our ice cream store, we were assuming that there was a linear relationship. By what I mean linear is that I could draw a line between my people in the store and the temperature. This relationship does not apply to all machine learning problems. For example, let's say the amount of water that a human must drink. I think we can all agree that drinking no water is very bad for you. That I believe it's recommended that we drink 2 liters of water per day. That is good. But again, if we start drinking too much, let's say 15 liters of water, that this again starts being very bad for your health. If we were to map this then with maximum health points being Y, and the amount of water we're drinking being X, then we'll notice that our relationship is something like this. We can start 0 here, we know it's bad, so that will give us negative health points. We can agree that there's a sweet spot here on the 2 liter mark, where our health is at its maximum, and then the more we pass the 2 liter mark, we start over drinking, that our health point starts going back to 0. We can see here that this is not a linear relationship because I can't draw a straight line. I have instead a parabolic line or a quadratic relationship. It's a non-linear relationship. This makes a few things. On my example before, I could kind of easily tell you, and it was easily understandable, that if I remove 1 Celsius, or if it was 1 Celsius cooler on that day, that I will maybe have less 15 people on my store, because it was linear, right? The change I was making on the temperature, it was easily applied to the change of people in my store. In a case like this, where I have a nonlinear relationship, this, what we like to call in the industry, explainability, becomes a lot harder. On the next episode, you will see that for neural networks, we're dealing with very non-linear complex relationships with data, which does not make it very clear on how they're interacting with each other. We'll start explaining why data scientists and researchers in general, they're not very sure of how the model is coming to this conclusion, but that is still, at the end, mathematical computations. And just like we're showing here, where we have to find our m's to our features, even your ChatGPT at the moment and your other LLMs are just your m's and your features. And in fact, if it's anything interesting for you, you're wondering how many features there are. Well, every time you see 8 billion parameters, 10 billion parameters, or as estimated on the big models like GPT-5, they are expecting 1 trillion parameters. So yes, that is correct. It would mean that to get your Y, they're having up to 1 trillion M's with 1 trillion features. Not exactly like this. I'll explain a bit more on the next video. I hope you've learned something. And if you're more interested in going more detail, I recommend you search gradient descent, which is the technique that I showed you on this video. Thank you for watching. Please like and subscribe. And if you have any feedback or any comments or any doubts, feel free to leave a comment and I'll answer as fast as I can. Thank you.